picking right up where we left off. Let's check in on these learning goals. Pretty short and sweet. So be familiar with the historical context of MO theory. So I went through that last week in the valence bond theory lectures. And, this isn't a history class, but to have some familiarity with the folks and the people who worked on this stuff. So be familiar with the LCAO-MO method. So I was just going through that, the linear combination of atomic orbitals to form molecular orbitals. Be familiar with the bonding and anti-bonding wave functions for H2+. And so really all I want you to recognize there is for H2+, we create a bonding wave function, psi plus, and an anti-bonding wave function, psi minus. And we're going to keep going with that, and we're going to see that it gets a little bit more complicated when we try to move beyond H2+, as you might guess. Okay? So be familiar with the overlap and anti-overlap integral, and really just being familiar with the concept of this, that it's really that this overlap integral and anti-overlap integral is describing either the constructive or destructive interference between the internuclear zone. Okay. Be familiar with the energy solutions for bonding and anti-bonding and know what their graphs look like. So that's the important thing, is to recognize what a bound state looks like in terms of its energy solution and what a repulsive state looks like in terms of its energy solution. Well, so that's 5 of our 8 and only in one lecture. So the rest of the lectures this week on MO theory are going to be constructing MO diagrams and putting together molecular term symbols. And I'm going to take my sweet time going through that stuff. Some of it's going to be review. Some of it will be new. Okay, so let's go for it. So describing how we create an MO diagram. So I should write that there, MO diagrams. Okay, so electrons supplied by atoms are accumulated in orbitals to achieve the lowest energy configuration, subject to constraints by Pauli. Okay, so we know that the bonding configuration will be the lowest energy configuration. The anti-bonding configuration is the highest energy configuration. So our goal is to try and minimize energy. So if several degenerate orbitals exist, then electrons are added singly to each individual orbital before doubly occupying any one orbital. That's what that should say. Any one orbital, okay? If 2 electrons do occupy different degenerate orbitals, okay? So let's be very careful about this. So they could be degenerate, so same energy, but they are different orbitals. And so a good example of this would be like px and py, okay, for example. So a lower energy is obtained if their spins are parallel. So in other words, not paired up, but both going in the same direction, right? Which creates the triplet states. So up, down, or the superposition of either state, okay? So a triplet state in molecules actually makes a lower energy state than a singlet state. That's contrary to what you might expect. You might expect, 2 paired electrons being a singlet to be the lowest energy state. And that's true if that's the only option for the electrons, right? Is that they both have to occupy the exact same orbital, then the lowest energy configuration will be achieved if they're singlets. However, if there are different degenerate orbitals that the electrons can spill over into, a triplet state will be the lowest energy state, okay? So let's talk about sigma orbitals, all right? And so we've talked about sigma bonds with valence bond theory, right? We know that a sigma bond is symmetrically cylindrical, about the z-axis. And you can see I've got that right here on my Mathematica file, right? We know that we create a bonding sigma orbital from constructive interference, and we create an anti-bonding sigma orbital from destructive interference. But now what we need to talk about is their symmetry, okay? So as it turns out, a bonding sigma orbital has what we call even symmetry, which in the German is Gerard, okay? And we create this even symmetry by drawing a plane through the center of the internuclear axis. So I'm drawing a line right down the internuclear axis, and I start below that line and go above that line. And if the wave function does not change signs when I go above and below that line, in other words, if they're both positive, then it's called Gerard symmetry. Okay, and so our, when I earlier alluded to that we were going to use the 1 sigma g, that's where that g comes from. So our bonding sigma orbital is 1 sigma g. But now if we look at the symmetry of the anti-bonding orbital, right, we recognize that it's destructive interference. So there's a positive and a negative overlap, which is what creates the destructive interference. And it doesn't matter which one you ascribe to be positive or negative, because we know since it's this anti-bonding orbital with destructive interference, it has to change signs. That's why it has that destructive interference. So that is called odd symmetry or ungerard, and that's designates the anti-bonding orbital as 1 sigma u. Okay. So now we create a molecular orbital diagram. So I'm going to start on the left by kind of showing you like my, this is a diagram from my Gen Chem notes. And then I'll show you the more simplified version of it on the right there. Okay, so we have our 1s electrons, right? And I've got my model in front of me. So if I back up here, you can see exactly what this is creating, right? We've got 2 separate 1s electrons, which are given right here. And, the reference of those is, I'll remind you, like if I look at my bound state, okay? Right, the reference of that is given as the 0 line. So I could say 1s down here and 1s down here. And now down here, I make a sigma, and I'll just use the nomenclature that we talked about, the 1 sigma g. But you notice right here in my Gen Chem notes, it says sigma 1s. So, right, it's the 1 sigma g. Okay. But this diagram, it literally has its origins from this Lennard-Jones potential well. We recognize at infinite separation, the energy is just equal to the 1s energy, right? And there is some minimum energy, okay? We also remember that there's an anti-bonding state, right? This repulsive anti-bonding state that we now know is the 1 sigma u. And if I do what's called this vertical transition where I go straight up, then that line right there, which we can see right here, corresponds not to the minimum, it just corresponds to the vertical transition of the antibonding state. In this case, sigma star 1s. So oftentimes if we see a star, that also denotes antibonding. And we have 1 electron from our hydrogen 1s. We have another electron from the hydrogen 1s. And those combine to pair up because they have to, right? If I put 2 electrons in this bond, we still are subject to constraints by Pauli. So the H2 has to make a singlet state, right? And so we could write our H2 molecular electron configuration as 1 sigma G2, okay? So that's how we would write our molecular electron configuration. And we recognize that it is making a singlet state because they're paired up. So the simplified diagram looks something like this. where we've got the H1s and the H1s, and the 1 sigma G and the 1 sigma U. We know that there's an electron over here and there's an electron over here, and they spin correlate to make a singlet state. Okay? So we can also use these diagrams to describe why certain molecules don't exist. Okay? For example, we know H2 can exist because according to my diagram right here, it's all bonding. And so I forgot to put the formula on here, but we can come up with something called bond order, okay, which is given as the following, B, and that's going to be 1/2 times the number of, let's see, all right, bonding electrons minus the number of anti-bonding electrons. So if we do that for H2, we can see that there's 2 bonding electrons and 0 anti-bonding electrons. So B equals 1/2 times 2 minus 0, and that equals 1. And so a bond order of 1 means that, yep, it's just a single bond, H bonded to an H. Okay? He2 cannot exist. And the reason why it cannot exist is because of the following. So we know that each H1s brings 2 electrons to the table, and each H1s, of course, is a singlet state in its ground state. And so now, because each H1s brings 2 electrons to the party, I've got to supply 4 electrons into my orbital diagram. So I go 1, 2 in the bonding, and I've got 2 left, and those have to go in the anti-bonding. And so now my bond order for helium-2 is going to go as 1/2 times 2 minus 2, which equals 0. So helium-2 can't exist. Okay, hopefully you remember that. And also, if you might kind of guess, you might remember this intuitively, when you go to look at all the other noble gases, all of the other noble gases will be completely full shell. So their bonding electrons and their anti-bonding electrons will cancel out. So none of the noble gases exist as diatoms. Okay, hopefully you remember that. So moving on. Okay, so there's more than one way to create a sigma bond. And this is where this can get a little confusing. So to make a sigma orbital out of anything but H2, we technically need 2s and 2pz, or even 3s and 3pz, or 4s and 3pz, and so on and so forth. Okay? So H2 is literally the only thing that we can make a sigma bond using 1s electrons. Everything else, it's got to be higher order. So now if you look at, so this is the 2s and the 2pz superimposed, and I'm going to do the same trick here, right, where I've got atom A and atom B, and we're going to make them scale in and out of each other. Well, if you look at the complete basis set for this, okay, right, we've got some normalization constant times the wave function for A2s and B2s and A2pz and B2pz. We can actually separate these into 2 separate basis sets. And again, following the LCAO-MO, the linear combination of atomic orbitals, because we don't know which is which, we get this plus-minus state. And so we're going to call linear combinations of 2s also the 1 sigma G and 1 sigma U. We note that hydrogen is the only one that has 1 sigma G and 1 sigma U from linear combinations of 1s wave functions. Everything else is linear combinations of 2s wave functions. All right? And so this plus or minus state will create the 1 sigma G and the 1 sigma U, bonding and anti-bonding. But now, what if I combine 2pz? Okay. Well, hopefully what you remember from the valence bond theory, when I orient 2pz orbitals towards each other and they combine, they make a symmetrically cylindrical electron density about the internuclear axis, right? So here is my Z axis once again, and there's my nuclei B, and there's my nuclei A, and I even have this down here on my model. Let's find it. Let's see, here we go, right? So here are two p orbitals, right? So you can see in this case, they're oriented on that Z axis. And now as I get them close to each other, they create this enhanced electron density in the internuclear zone. So that is also a sigma bond. You also notice there's electron density on the outsides right there. And typically those are where lone pairs can exist, okay? And so now if I consider my symmetry operations here, right? So I drew my Z-axis. So we note that when I combine A plus B, okay, and I look at this symmetry operation, that's going to have Girard symmetry, which is why we call it the 2 sigma G. But now what about the anti-bonding? Well, so here I've got the anti-bonding model for 2 sigma. And you notice here now when I try to get those close to each other, once again, that anti-overlap integral really takes over and pushes all of that electron density out to the other regions. And of course, the more they overlap, the more that positive and negative will cancel each other out, owing to an anti-bond. So when I do a symmetry operation here, and again, nuclei B and nuclei A, there's a change of sign when I cross that center of inversion. So that means the anti-bonding for 2 sigma also has un-Girard symmetry, okay? So when we combine 2s and 2pz, we get 2 separate basis sets. We can make a 1 sigma g and 1 sigma u out of combining the 2s. And we can make a 2 sigma g and a 2 sigma u out of combining the 2pz. And of course, the plus state will give us bonding, and the minus state will give us anti-bonding. All right, so continuing along. So here's some pictures from my, like I said, from my Gen Chem notes, which you can see in the simulations, but just to summarize, to go through this, right? We can make sigma bonds from all of the following: a 1s plus a 1s to make a sigma 1s bond, and I'll note that that's called the 1 sigma G. Okay. If we do the minus state, a 1s minus a 1s, we know that that makes the sigma 1s, which sigma 1s star, which we could also call the 1 sigma u. All right. And then of course the same is for 2s, so I'll just say same for 2s linear combinations. They still make what we call the 1 sigma g and the 1 sigma u. When I make linear combinations of 2pz and 2pz, I make the sigma 2p bond. In Gen Chem, that's what we would call it. The more correct name would be 2 sigma g. And of course, I can make this anti-bond just like I showed you from subtracting these. I could call it the sigma 2p star in my Gen Chem book, but the more correct nomenclature we use for spectroscopy, 2 sigma u. Okay. So what about pi bonds? What happens when we make pi bonds? Okay. Well, just like we talked about in valence bond theory, these are linear combinations of now p electrons that are off axis. Right? So remember, my internuclear axis, I'm going to draw this way. Okay, so there would be my A nuclei, and there would be my B nuclei. And as I scale these close together, you can see here, I'm going to make a lovely pi bond on my Mathematica model here. We're waiting for it to calculate. Beautiful. And I think if I get it a little bit closer, it'll look like the classic pi bond. Okay. Yep, so there it is. Lovely. All right. And so we're going to call this, pi 2p in the Gen Chem days. But as I'm going to show you here in a moment, this is technically the 1 pi u. Okay, so let's take a look, right? So here is the linear combination I just made. 2p orbitals oriented in the same direction, right? With both positive lobes going. So we know that when we bring these close together, as shown here, the positive and the positive region will constructively interfere, and the negative region will also constructively interfere, which is why I get this picture right here. I get, lobes on either side of the internuclear zone. Well, if you look at my symmetry operation, that means my bonding state for pi bonds technically has odd symmetry. So we got to keep track of that. It's the opposite as the sigma bonds, right? And of course, I can't show you this on my model because my model is technically only 2-dimensional instead of 3-dimensional. But I could also make another set of pi bonds with 2 pi y. Okay, so over here, I'm going to call this 1 pi xu. Okay, and then I could also make another pi bond, which would give me a triple bond, right? If I had 1 sigma and 2 pi bonds, I'll call this the 1 pi yu. And we don't know which is which. It doesn't matter which one we call x or y, but what's important to note is it's not z. The 2pz makes a sigma bond, right? The 2px or the 2py make our pi bonds. And so now if we look at the anti-bonding state, let's go look at that. So that's going to be given by the subtraction. So you can see I've got it here. But now if I separate them, I've got 2 separate p orbitals. Okay, we'll let it calculate. And as I get them close to each other, they interfere destructively. So there's no enhanced electron density that's created between the 2 nuclei or even off axis from the 2 nuclei. I get these kind of 4 independent lobes that you can see right here. And it'd be the same situation for px or py. And then also, if we notice the symmetry operation, right, so we can see why these are anti-bonds. When I get these 2 things closer and closer, this positive lobe and this negative lobe interfere destructively, as well as this negative lobe and this positive lobe. So you can see that those have even symmetry. And so that's what makes this now the 1 pi x g and the 1 pi y g. Okay? So moving on, when we put all of that together, so follow with me here. So I'm going to stick, so first I'm going to describe this one on the right, and then I'm going to describe this one on the left. So as I go up in energy, right, I recognize that technically I would also have a 1s and a 1s down here in the core. But of course, for molecules, those aren't going to make any bonds, right? It's my valence shell that are making my chemical bonds, right? All the same, if I go up and describe the 2s and the 2pz linear combinations that we just talked about, we can see if I combine a 2s and a 2s, the 1 sigma g is the lower bonding energy. The 1 sigma u is the upper anti-bonding energy. Okay. Now, when I get up into the 2p level, here, and then pay attention to this. This is for more than half-filled p block. Okay. For more than half-filled p block. I'm going to get to my little description here. Yes. Okay. So when the p block is, really I should say half-filled or more, the 2 sigma g ends up being the lowest energy. And remember that 2 sigma g is created from linear combinations of 2pz. And so here I've got the 2 sigma g way down here. And as it turns out, the 2 sigma U is the highest energy up here. Also, I can make pi bonds from those off-axis electrons. And so again, for more than half filled, or for half filled and more, we would now get the 1 pi xu and the 1 pi yu. And what's important to note is 4 electrons can go in this level, right? We know 2 electrons in each orbital, but those count as 2 different orbitals. So I can get 4 electrons in this level, and I can get 4 electrons in this level. Keep that in mind, okay? And of course, the 1 pi xg and the 1 pi yg, remember the g's are the antibonds for pi. So now, as it turns out, for less than half filled, we can get S and P mixing. So let's see, S, P mixing can occur here for less than half filled. And so the result of that is it actually greatly reduces the energy of the pi bonds. I'm going to show you that in a moment. It's not that the 2 sigma G energy increases. Rather, it's that now this S and P mixing really reduces the energy of those pi bonds because of there being less interference in that internuclear zone. Okay, and so now what ends up happening is the pi bonds get lowered way down there. So we got 1 pi xu and 1 pi yu, and then it goes 2 sigma G, then 1 pi xg, 1 pi yg, then 2 sigma u. Okay, so let's do an example. So here's oxygen, and so we know that each oxygen contributes, let's see, quick flash. So we know that each oxygen is going to give us 6 electrons each, right? If I look at my oxygen, you know, atomic energy diagram, so it's 2s and 2p, and there's 1, 2, 3, 4. So each oxygen is going to bring 6 valence electrons to the party. So I'll populate those over here in my AOs. Okay. So I'm just going to put them all here so I know that I've got to use them. And so now that means I'm going to have 12 electrons that I occupy that I bring down into the MOs. So I've got 1, 2, 3, 4 to take care of with the 2s, and there's 1, 2, 3, 4. Okay, great. So that 1 sigma G, 1 sigma U is all blocked up. So now what about this lower level? Well, oxygen is more than a half-filled p block, and because it's more than a half-filled p block, the 2 sigma G is lower. Okay? And I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons that I can populate in here. And so that's going to go 1, 2, and then I'm going to be able to put 4 in this 1 pi u, right? And then that leaves me 2 more in the 1 pi g. So now what about the bonding order of oxygen for this? Well, 1/2 times, and I've got 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, and I've got 1, 2, 3, 4 anti-bonding electrons. 8 minus 4 is 4, times 1/2 is 2, and we know oxygen has a double bond with 2 lone pairs, and as we even can see right here, technically O2 is a triplet ground state. 2 unpaired electrons. So it's a triplet state. We could also call it a diradical. And also we recognize that oxygen is paramagnetic because it has those 2 upspin electrons. So if the electrons were spin correlated, then any magnetic moment would be canceled. Okay? So we learn a lot from these MO diagrams. We can predict a lot about the chemistry of things. And the fact that this is a triplet diradical state, it makes O2 extremely reactive, which hopefully you remember as chemists, or you know as chemists, O2 is very reactive. Okay, so let's look at the series of simple homonuclear diatoms. And oh my, wait, no, I lied to you guys. I knew I had that backwards. So I'm sorry about that. S and P mixing can occur, and it's the S and P mixing that greatly lowers the 2 sigma G orbital. I knew that that didn't make sense when it came out. So S and P mixing can occur, lowers 2 sigma G. Okay, apologies there. So now if we look at Li2, Be2, B2, etc., right? So you can see for the most part, the as we get to more electronegative elements, those bonds lower in energy. And you can also see this 2 sigma G, right? This is what really, really starts dropping down as we go into the more than half filled, okay, situation. And so as we populate electrons through, what I want you to keep in mind is we want to really keep track of where we put all of these things. So 1 pi u, 1 pi g, 2 sigma g, 2 sigma u. Because where I'm going next with this thing is describing polar bonds and how we do molecular term symbols. Okay, so that will be in the next video. So that wraps it up for homonuclear diatomics. So be able to construct these molecular orbital diagrams. Where I'm going next is describing heteronuclear diatoms. Okay? All right, folks, I'll see you later.